here's the deal. I have a great question for you today. We're going to be using complex numbers and geometry and all kinds of stuff. Buckle up, buckaroo. This will make sense in a second, all right? So we're told that root 3 plus I is the vertex of a regular hexagon centered at 0, 0. Okay, so there's going to be 6 corners. This is one of them. And centered at 0, 0, we're going to generate a regular hexagon, which I will do in a second. Now, each of those 6 vertices, like this complex numbers that represent the vertices, are all going to be raised to the power of 4. Our job is to find the area of the new shape. Let's go. Now, let's form a hexagon. So what it means is, first of all, very quickly behind the scenes, I realized that root 3 plus I has a modulus of 2. So everything about my regular hexagon is going to have a modulus of 2. This also has an argument of, I want to say pi over 6. It has an argument of pi over 6. Now, how do we generate? And I suppose we could write this as 2e to the I pi over 6. There we go. Now let's find the other vertices. Now graphically we can do this. There's going to be one directly opposite right there. Now I need to split it up. Well, what we're going to do is we're going to go every 2 pi over 3. Every 2 pi over 3, 120. Yes, 2 pi over 3, which is 4 pi over 6. So we need to do 5. No, pi over 3. I need to go over pi over 3. So 1 there, 1 there, 1 there, and 1 there, I do believe. All right, and we end up with our hexagon. This looks quite nice, actually. Not my worst bit of drawing. Not my worst bit of drawing. Now, the real thing to realize, of course, is that that is pi over 3, pi over 3, pi over 3. All right, so these points are spread every pi over 3. Now, we know, luckily for us, is how to generate that. If I want to rotate a point, by pi over 3, what do? I'm going to multiply it by ei to the pi over 3. And I can do that every single time. Now, it might be worth noting that pi over 3 is 2 pi over 6. That's going to make my life a little bit easier. So where are my vertices then? I've got 2 ei to the pi over 6. We'll go another 2 pi over 6. So that's pi over 2, which is that one. 2e to the I, let's add another 2, 1. That's 3, so 5 pi over 6. That's that one. So actually that probably should be a little bit lower, symmetrical actually. That would make sense, so there we go. 2e I to the 7 pi over 6, 2e to the minus I pi over 2, or 3 pi over 2. Depends really. I 3 pi over 2, and then 2e I to the 11 pi over 6. So those are my 6 vertices. Now what we want to do is we want to take them all to the power of 4. Well, let's do that then. Let's take them all to the power of 4. The modulus gets power of 4, so it's all going to be 16, 16, 16, 16, 16, 16. So power of 4, that's ei 4 pi over 6, because of course when I take something to a power, like we multiply. So 4 pi over 6. What's 4 pi over 6? That's 2 pi over 3, isn't it? 4 pi over 2 is just ei to the 2 pi, which is 0, I suppose. That's just going to be 16. We'll deal with that in a second. This is I to the 20 pi over 6, which is 10 pi over 3. Let's do simplify as we go. 28 pi over 6, which will be 14 pi over 3. 6 pi. And 44 pi over 6, which is 22 pi over 3. Right. Now, obviously, a bunch of these are bigger than 2 pi, so we're going to bring them all back down. This one looks legit. So that's 16e to the I times 2 pi over 3. That one's just 16. Okay, cool. 10 pi over 3. Well, I can take off a bunch of 2 pi's, which is 6 pi over 3. So that is 16e to the I 4 pi over 3. All right, taking away 6 pi over 3. Because we're going to keep it between 0 and 2 pi. That's what I'm doing here. Because I think some of these are identical. Okay, fine. I know some of them are. E to the I 6 pi, that's a bunch of 2 pi. So that's just going to be a 16. So already we can see these two become the same. And you're probably not surprised about what's going to happen here. I can take off 12 pi over 3 here. I can take out 4 pi, which is 12 pi over 3. So that's actually 2 pi over 3. So that is the same as that one. And I can take out a whole bunch of 6 pi's over 3. I can take away 18 pi over 3, which will left me with e to the I 4 pi over 3. If I express all of these great big angles in terms of 0 to 2 pi. So in fact, once I do this transformation and I take the power of 4 of all of this, what am I left with? Well, I am left with a triangle. I'm left with a triangle here. And let's try and draw this. So now I've got these points that are spread around. That's a bit iffy. They're spread around. They've all got a modulus of 16. My first one is at 16. Then I've got 2 pi over 3, which is up here. And the other one is 4 pi over 3, or minus 2 pi over 3, which is over there. So we end up with an equilateral triangle, which is the best I can do here. An equilateral triangle with a radius of 16. Now, the way to find the area of this bad boy is, of course, what we can do is divide it into 3 triangles, each of them with an interior with an angle there of 2 pi over 3, their length 16. So what do? The area is going to be 3 lots of this triangle, and each of those triangles is a half AB sine C. What's that? That's 3 times 8 times 16, 128, times sine of 2 pi over 3, which is root 3 over 2. Which is a half of 128 is 64. 3 times 64 is 192. So I do believe it's 192 root 3 unit squared. Did my brain stop braining somewhere here? But the really cool thing here, of course, is what we're playing with, is the fact that my hexagon, once I take the power 4 of all of these complex numbers, we end up with a triangle. So we're testing our understanding of an Argand diagram, we're testing our understanding of what happens when we take powers of complex numbers, and we're also testing our understanding of the arguments and how certain numbers might look different, but they're actually the same. Did I make a mistake down here? Let us know in the comments below. Maybe I left one in on purpose. It's always on purpose. Otherwise, subscribe, smash the like button, smash the notifications so you know when more of this is coming out, and I will see you on the flip side. Ooh, I didn't say that, did I? Ugh. Bye.